we're talking about dynamics today. Dynamics is why things moved. With the kinematics, we talked about how things move, where they are and all that. This is why they move, and the answer obviously is because something's pushing on it, right? You got all these forces. Newton used the word action, but today we kind of talk about forces. And the first thing that you want to do is say, what are all the forces that push on it? And then when you combine those, how is that going to change the motion, specifically the acceleration? So you end up drawing a lot of pictures like the ones that you see here. These are typically called force diagrams or free body diagrams. Either one works. But you've got this object. It's a free body. It can move in space, and you got to think about what's pushing on it and all that. So no big deal. We've got some variables that are kind of new to us here. Last time you remember that in kinematics we had x, v naught, v, a, and t, those five with their units. Well, we still have a. We're still interested in the acceleration, but we're also talking about F, the force. The force could be any kind of push, pull, any kind of action on it that's going to cause it to move. We measure that in newtons, and the capital N there is a newton. A newton is not a whole lot of force. If you're holding a ballpoint pen or something now, that's close to 1 newton of weight. Weight is a force, right? It's the force of gravity pulling down on something. So it's not a whole lot. 1 newton would be the force that would cause 1 kilogram of mass, we still got to talk about mass, to accelerate at 1 meter per second squared. The easiest way to remember this is the formula that I'm going to show you here. F equals ma. Well, if the mass is in kilograms, like you see right there, and the acceleration is in meter per second squared, then I'm looking at a kilogram meter per second squared, and rather than write that over and over and over, we just call it a newton. All right? So it's pretty easy to cook that up. Mass is a measure of how much stuff you have, how much matter there is. We don't measure mass in this country unless you are lucky enough to be sitting in a physics classroom. We use weight in this country, and weight is how much gravity pulls on mass. So they're related, but they're not the same thing. I'll put over here that weight equals mass times the acceleration due to gravity, mg. And we're going to use that over and over, but realize that mass is how much stuff you have, and weight is, if you happen to be standing on Earth, how much is gravity pulling on it. If you went out into space, you'd still have the same amount of mass, but very little weight. We say weightless, right? Virtually zero weight. So these are related, but if the g goes away or changes, then the weight's going to change too, even if your object doesn't. The acceleration, we're familiar with that. Meter per second squared, same thing it was last time. Got one more here. This is the Greek letter mu, the lowercase mu, and that stands for the coefficient of friction. There is no unit to the coefficient of friction, which is kind of interesting. Everything else in physics, not everything, but almost everything else has some kind of unit. This one does not. So we'll talk about that too. The main formula, like we said, is that the force is equal to the mass times the acceleration. And that little mark out in front is the Greek letter sigma, which starts with S. And so we use that to sum, to add up. You could write this the net force, the total force, the vector sum of all the forces is equal to mass times acceleration. These are vectors. We didn't really get into vectors last time. We won't this time, but you could write it like that, saying that these are vectors here. And the net force, when you add all the forces together, you know, some of them are going to cancel each other out, but the ones that don't are going to determine the acceleration here. So that's where we go. This is called Newton's second law, and it's a big deal. Okay, he had 2 other laws. This one is the big deal. So here's a typical problem. If you had an airplane and it's getting pushed, we'd like to know how much it accelerates. Down there at the bottom you see Newton's second law. So like we did last time, I'm going to draw a picture, and you could get all fancy and draw an airplane here if you want. You could draw a box. I don't really care, but somehow you need to say I have an object, and whether you say it's a box or an airplane, whatever, you need to put all the forces that are acting on it. So if you're thinking about the airplane, there's 300 newtons, and we'll say it pushes this way. All right. If you just draw the box, who wants to draw airplanes, right? Draw a box. I don't care. Put a dot. I don't care. But you need to have, here's my object, here's the force on it, right there. Okay. Now that took care of that. The 300 newtons. Remember how we're always looking for the numbers, and here's another number, so we need to do something with that. That's in kilograms, so that's the mass, and whether you want to put it up here, draw the airplane, or down here, same difference. I have to draw this picture so that I know what the object is, and I know what all the forces on it are, and then I can use Newton's second law to say F equals ma. I know the force, I know the mass, I want the acceleration, and solve for that. I'd have to divide both sides by m, and my force was 300 newtons. My mass is 4,000 kilograms, and 300 divided by 4,000 is 0.075. Okay, so that's not a very big acceleration. What would the units be on that? It's supposed to be an acceleration, so it should be meter per second squared, but I got this Newton per kilogram. Wonder what that is. Here's a Newton per kilogram, and I remind myself that a Newton is really a kilogram meter per second squared, and when I put that on top of a kilogram, the kilograms cancel. Meter per second squared, that's what we wanted. So let's put that on there. Okay, so that's our first little problem there. There's only one force, there's only one object, so no big deal. Some of these problems have a couple objects. You could have two boxes that are tied together or something. You'd have to draw two objects and all the forces on the first one, all the forces on the second one. But for every problem on this test, somewhere you need to draw each object, and that could be the plane or the box or whatever. Okay, so we've done this. We need to draw all the forces, draw arrows representing all the forces acting on each object. So remember we drew the little force right there. This was the mass, there's the force. So now I've got that. I want to look at my picture and use sum of the forces equals mass times acceleration for each object. So I'm always starting right here like that. And then I go to my picture and say I've got one force, so when I add up all the forces, it's just that force. And I've got that. Solve the resulting equation. You'll get that equation right there. In our case, I think we knew the force, and we knew the mass, and we were looking for the acceleration. So we solved it. Okay? Every problem is going to work out just like that. Okay? So here is our airplane again. This time I've got three forces pushing on it. I don't want to draw another airplane. I'm just going to draw a box. And the three forces are 300 newtons forward. So I'm going to call forward to the right here. And if you want to give it a fancy name like F1, that's fine. If you want to just put 300 newtons, that's fine too. Okay, but there is my first force. And the second force is 200 newtons forward. And the third force is 150 newtons backward. Okay, can you see the value of that little simple picture right there? I have an object. I got three things pushing on it. I know the directions. I know the magnitudes. I can add those forces together and see what the total force, the net force, the sum of the forces is, and find out some stuff I didn't know before. I did draw the object. I did draw the forces. It's time to write sum of the forces equals mass times acceleration. And that's where I go back to my picture and I say 1, 2, 3 forces. I've got F1, F2, and F3, and together they're going to cause the mass to accelerate like that. Now I've got to put some signs in here, and if you think about what we did last time with the coordinate system concept, we said let's call everything one direction positive and everything that points the opposite direction negative. Now again, you kind of get to pick which way is positive and which way is negative, but my advice would always let the direction of motion be positive. It will work the other way. But if you just let the direction of motion be the positive direction, you can see that I've got 300 plus 200. I've got 500 newtons to the right, 150 backwards. It's going to move to the right. Or if it is moving to the left, it's going to be slowing down. It'll stop, and then it'll start moving to the right if the forces continue, right? So with this coordinate system here, everything that points right is positive. F1 points to the right, so he gets a plus sign. F2 points to the right, he gets a plus sign. But F3 is pointing the opposite direction, gets the opposite sign, a negative sign. And I have to manually put those in down here, like you see right there. But that's the thing. All right. I'm looking for A. If it were me, I'd go ahead and divide by M on both sides to get that A by itself. Okay, but I'm moving into the fourth step here, where I'm starting to solve this equation. I could put these numbers in. I could have 300 newtons. That's positive because it's to the right. I got plus 200 newtons, positive to the right, minus 150 newtons. I'm just using the signs I had up here. And then I'm dividing that by the mass, which was 4,000 kilograms. And they're telling me that's going to be the acceleration. Now, when I do this on my calculator, here's another one that's easy to mess up. Remember that I want to do all of this before I divide by 4,000. So, on my calculator, I am going to say parenthesis 300 plus 200 minus 150, and close up that top parenthesis, divide by 4,000, and I get a 0.0875. Okay, that's a little bit better than we had last time. It's still pretty slow. If you want to push a big old thing like an airplane, you need to put some force on it. Right? 4,000 kilograms, and that's probably a pretty lightweight airplane actually. You're gonna have to put some serious force on it. All right, but that's what you want to do. Draw the object, draw the forces, use that picture, your free body diagram, your force diagram, and plug it into here. If you have 1, 2, 3 forces, then you're going to have 1, 2, 3 forces. And it's that simple. 2 of them are to the right, so those 2 are positive. F3 is negative because it's to the left. Watch your signs, watch your units, all that, but it's not that bad. Here's a little list of possible forces that pop up in these problems all the time. So I'd like you to kind of think about this. If you want to write this list down and just kind of, every problem, just kind of go, do I need this one? Do I need this one? Almost like a little checklist, right? Is gravity an important force in this? The normal force. When I put a book on a table, here's the book right here, and it's sitting on the table, and that's not very good, is it? And gravity pulls straight down. Okay, so I'm going to put an mg there. That's the force of gravity pulling down. The normal force is the table pushing up. And we call it the normal force because in mathematics the word normal means perpendicular. There's a right angle between the normal force and the table. Even if you tilt the table, the normal force will still be perpendicular. It'll still go up like that. The weight still pulls straight down. Okay, so the book is here, and if I tilt this up at some angle theta, then the normal force is going to tilt so that I have a nice right angle between the table. Can't do it. Between the table and the normal force. But gravity always pulls straight down like that. Well, that book is not going to float up into the air, and it's not going to sink into the table. So sometimes the gravity and the normal force cancel each other out. In fact, if I came in here and said the sum of the forces equals mass times acceleration for this picture, I get two forces. The normal force is up, so we'll call that positive. Gravity is opposite direction, negative, down. And we already said that book isn't going anywhere, so the acceleration is 0. That means that the normal force is equal to the weight. Those cancel out. If they cancel out, they don't do anything. If they don't do anything, I don't need them in my picture. So very often you can just leave those off. But you should ask and say, do I need the gravity in this problem? Here's another problem. Maybe there's a box that's hanging from a string. So that string's holding it up, and gravity is pulling down. Okay? And maybe the whole box is moving down slowly that way. That's my direction of motion. You can see that the gravity is a really important part of that problem. As the box moves down, it's the gravity that's pulling it down. So I need that on there. But there's no table, there's no ground pushing up on that box. So I wouldn't have a normal force. You need to go through and say, do I have gravity? Do I have the normal force? Do they cancel each other out? If they cancel, don't put them. If they don't cancel, then you do need it. Okay? The string tension right there, I just put a T. That one had a string in it. If I were to reach up here and cut this piece of string, then that box would just fall. Right? So the string is slowing it down. It's an upward force holding that thing back, keeping it from going into free fall. A downhill pull. Anytime I put something on a ramp like this one right here, gravity wants to slide it downhill. So anything on a ramp, you can just point an arrow downhill and say, well, that's my downhill pull. And then you can do some math and show that that's always equal to mg sine theta. Okay? Anything on a ramp is going to have a downhill pull, and guess what? It pulls downhill. All right? Friction is a possible force. Now, they're going to give you a coefficient of friction. Remember, we saw mu before. So there's kind of three possibilities here. Usually, the friction will either be mu mg or mu mg cosine theta. This one on a flat surface, this one on a ramp. If I were drawing the friction in right here, let's say I'm pulling this box uphill. If the box goes that way, then I would call all the forces that pull uphill positive and anything that pulls downhill negative. So the downhill pull is negative there. One way to think about that is slowing it down. It's removing, it's subtracting speed. Okay, so when I put it in, it needs to be a negative. The friction is also backwards, slowing it down. The force of friction, F sub F. And because I'm on a ramp here, because nothing else is pushing up or down, then I'm going to get mu mg cosine theta. Okay? Whereas if I drew the friction on this one, let's say this guy's moving to the right, the friction here would point backwards. Friction always fights motion. So here's F sub F, and because that one's on a flat surface, that one would be mu mg. Okay, now there is a third possibility. If somebody came along and sat on this book, that would push it down harder on the floor. That's going to make it harder to move. So the friction would go up. If you have any kind of vertical forces, like a person sitting on the book or a box or a sled, or if they're lifting up on the front of a box and dragging it, those would be vertical forces that I need to put in there. So there I'd have to find the normal force first. Remember how we did it right here? It'd be a real similar process to that, except now I might have another, here's a guy sitting on it. So I'd have to come in and say, well, I got another, force of the person sitting on this thing. And then I'd have to, I'm going to add that to both sides. See how it changes my normal force there? I'm only interested in the normal force because the friction is equal to mu times the normal force. When the normal force was mg, then the friction was mu mg. And over here, we do a little thing with the rotated coordinate system, and there's a cosine theta in it. But any other forces, we need to go find the normal force and then use it here. All right. Last, when there is any kind of external force, maybe there's a string pulling uphill. Something's got to, if the direction of motion's uphill, something's pulling it up this way. Maybe it's a string, or maybe it's a person that's grabbed the book and dragging it. That would be some kind of external force. All right. So just read the problem, go through the list, and say, do I need gravity? Well, gravity pulls, but the normal force does, so I'm not going to put either one of those. There's no string, or there is a string. It's not on a ramp, so I don't have a downhill pull. And just kind of find the ones that you need. Let me do this little problem right here. This is called an incline plane problem. And if I have a 4 kilogram box on a 20-degree ramp, let's draw that much. Here's my ramp. Here's my box. Okay, the mass, we'll call this mass 1, is 4 kilograms. The angle of the hill is 20 degrees. And so I've got this number, and I've got that number in my picture. The coefficient of friction is 0.3. Remember, that's mu. So down here I'm going to put mu equals 0.3. That's a number that says how hard is it to move this box when it's in contact with that ramp. If you take your calculator, and you can do this at home, take your calculator and put the rubber sticky feet on the back down on the table. Try to slide that thing. It's really hard to slide. Then take the same calculator, turn it over on the same table, and it's got the hard plastic keys on the tabletop. And then all of a sudden it's real easy to slide. That's that coefficient of friction. It's a number that says how much friction is there between the two materials, between squishy rubber, sticky rubber, and the tabletop, or hard plastic keys in the thing. So typically there's a table, and you go look these up, or the problem gives it to you, something. All right. Talks about a string that runs over a pulley to a hanging box. So I'm going to draw the string. Come in. Stop. And here comes that string like that. It goes over a pulley and down to a second box right there, which I'm going to call mass 2. And they tell me that that has 11 kilograms. Okay, so this has got a lot going on in it, but you see how the picture kind of makes it real, and we can kind of make sense of this thing. Just draw it out, whatever they say. Draw a little picture so you can see it. That's the first step. Draw the object, or in this case, the two objects. Let me come back in, let's say, red here. I am interested in this box. Okay, never mind. Tell you what, maybe let's see if I can get a little 1 in there. Well, we already put mass 1 there, but if this is box 1, this is box 2, those are the two objects that I'm interested in. And then the next step was to draw the forces on each object. So I need to go through this list and say which forces pull on mass 1, and then I need to go through the list again and say which forces pull on mass 2. And then I'm going to build two equations, because that's step 3 over here. And then once I've got my equations, then I can solve them, all right? But that little list to keep you going straight. So let's get busy here. Does gravity pull on mass 1? Well, yes, it does. It's going to pull straight down, m1g. Okay. Does the normal force act on that? Is there a table? Is there a ground for this to push on? Absolutely. Okay, so there's the normal force. But again, it's not moving up or down. It's not floating off of the ramp. It's not sinking into it. These are going to cancel. And so I can leave them out of my picture. All right, I put dotted lines because I wasn't going to keep them. All right, I'm going to put an X here and an X there. I don't really need that in my picture because those are canceling out. Is there a string on mass 1? Yes, it is, and that's the force that's pulling this guy uphill. So I definitely need that. Anything that pulls it uphill, downhill, I need T. We got that. Is there a downhill pull? Is it on a ramp? Yeah, it is actually. So there's the downhill pull. I'll check that one. I do have friction, and the way that I know is because they told me there's a coefficient of friction, right? So yeah, that's one that's got to go on there. And the box is moving uphill. Friction's going to fight that. It's going to go backwards. All right. Do I have any other forces? Is there a human that's reaching in? Is there a winch? Is there a motor? Didn't say anything about any of that. So that's my picture right there. And the next thing I want to do is the sum of the forces equals mass times acceleration. And I want to do that for box 1. So sometimes it's good to come in here and put a little subscript. The sum of the forces on box 1 would be equal to mass 1 times the acceleration. Okay? And that's where I look back at my picture and say, I see 1, 2, 3 forces that are going to slide that thing uphill or downhill. T, DHP, F sub F. I'm just looking at the picture, making a little list. 1, 2, 3, 1, 2, 3. Equals MA because Newton said so. M1A. All right. Now here's where I come in with my direction of motion. And I say this box is moving uphill. So I'm going to call uphill positive and anything downhill negative. T is in the positive direction. Downhill pull is slowing me down, subtracting. Friction is slowing me down, subtracting. And there's my equation like that. I can fill in a little bit of detail on that because we know that the downhill pull was mg sine theta, and the force of friction on a ramp was mu mg cosine theta, and that's equal to ma, and all those could have 1s in it. Wouldn't hurt a thing. Okay. I have some of those numbers. This would be T minus 4 kilograms times 9.8 meters per second squared times the sine of 20 degrees minus 0.3 times 4 times 9.8 meter per second squared. This looks big, bad, nasty, but you know what? You're just putting in numbers. And they're all about to boil down. Right here. Can you see that all of that is going to be a single number? Now you need to be careful. They're both negative, right? So when you get your calculator out, first of all, it wouldn't hurt to check that you're in degrees, because we're about to put 20 degrees in here. But I'm going to start with that negative. 4 times 9.8 times the sine of 20. Started a parenthesis, I need to close the parenthesis and say minus 0.3 times 4 times 9.8 cosine 20. You can close that off if you want. But that's a negative 24.5, let's say. Negative 24.5. That is going to cook down to T minus 24.5 equals 4a. A lot of times I'll leave the units out here if everything's behaving itself up there. Okay. It just makes it a little cleaner. Ta. I got 2 unknowns, so I can't solve that. That's bad. When you get stuck like that, what you got to go do is build a second equation. So I go through the list again. Does gravity pull on this thing? Well, yes, it does, and that's an important force because that's what's making the whole thing move. The gravity pulling down on that is really important, so make sure you get that. Is there a normal force? No, because there's no table, there's no ground pushing up on that thing, which is what supplies the normal force. How about a string? I do have a string, and it pulls upward. It slows it down. Again, if I were to cut that string, this box would fall a whole lot faster. So the tension there is slowing it down. All right, so I put that. Is it on a ramp? Is there a downhill pull? No, it's not on a ramp. Is there friction? No, because it's not touching anything. It's touching the air. There is a little bit of air resistance. We're not doing that, okay? And there's nobody pulling on it, pushing on it. There's no motors, winches, anything like that, all right? So those are the only two that I need, the tension and the weight right there, okay? And now we want to build an equation for box 2. It's going to look like that. And I see T and M2G. T, M2G. Made my list, filled it in. I got to get my signs in there. Okay. Now, remember how we said that the T was adding to the acceleration? It's making this box go faster and faster, so this was a positive. And we said that the gravity is trying to drag it backwards, slow it down. The friction's trying to drag it down, slow it down. The one that's speeding it up here is M2G. So you got to be careful here. The coordinate system has to run this way. Okay? Both boxes move in the positive direction. And it's important that you set it up this way. The box goes uphill, so uphill is positive. This box goes down, so down is positive. That means that M2G, the one that's adding to the speed, is positive. T, the one that's subtracting, slowing me down, holding me from going into free fall, is got to be a negative. Okay, so that's the way you've got to set that up. The other way that people think about this sometimes, you've got one coordinate system, it goes uphill, and then it's going to keep going uphill, and when the string bends around the pulley, the coordinate system bends with it and keeps going down like that. All right, either way is fine, whatever you want to do, but you got to get those signs right. And I'm going to show you a safety check here on it in just a second. This was 11 kilograms times 9.8 equals 11A. I don't know T, I don't know A. All I can really do is say 11 times 9.8 is 107.8. So we could fill that in. Okay, but essentially I've got this equation and I've got this equation down here, and I can't solve either one of them by themselves, but when I put them together, then I can. And it would be nice to have another screen here, but I don't. So what I'm going to do is I'm going to take this red equation and write it right underneath here. And this is going to kind of make a mess, but I'm out of room, so I'm just going to do the best I can. Here is that positive T minus the 24.5. That's equal to 4A. And those are two simultaneous equations that we want to solve. Like that, a system of equations is another name for it. You could do the substitution method, solve one equation for one of the variables, plug it into the other one. You could do a matrix thing. You could do Cramer's rule. You could do row operations. You could do reduced row echelon form on your calculator. You could do anything you want. But the easiest thing in the world is to take this equation and this equation, draw a line, and add straight down. Okay? That works because the left-hand side of this equation is equal to the right-hand side of that equation, and the left-hand side of the second equation is equal to the right-hand side of the second equation. So when I add all this to that, and 4A to 11A, I am adding the same thing. It's equal, right? Adding the same thing to both sides. So this is perfectly valid to do. If you do that, see how you got a T minus T? And those T's are going to cancel out. If the T's don't cancel out, you goofed up your coordinate system. The T's always cancel out. that means there's nothing but A left, and I can solve this really easily. 11A and 4A, when I add that, I get 15A. 107.8 minus 24.5, somewhere around 76. Let's see what we get. 24.5. 83.3. Okay. Forgot about the 7 there. 83.3, but it's still kind of close, right? Divide by 15. It's good to know kind of where these things should end up, and then if they don't, kind of fix it. When I divide by 15 rather, I get 5.55. You can see that all I did there was divide both sides by 15 to get A by itself. 5.55 equals A. That's the acceleration. Sometimes on these problems they want you to find T as well. How much force does the string have to be able to supply? If you take that A and plug it back in right here, then you could solve for T. Or I could take that A and put it in right here and solve for T. You'll get the same answer if you do it here or there. But just plug, once you got one answer, put it back in wherever it needs to go. So that's all of that. Here's the little summary. And dynamics is all about why things move. It's because of the forces, and you got to add up all the forces. You got these variables F, M, A, and mu with the units, so you got to kind of know what those are. But there's really only one formula that we're adding here. And every problem, you're going to draw each object. You're going to draw arrows on each object that represent all the forces, and you got that list down here to kind of guide you through that. You need to look at your picture and use sum of the force equals mass times acceleration. That's how you're going to build the equation right there. Newton's second law. Okay? And whatever equations you get, you solve for that. Again, gravity, mg, the normal force, F sub n, only if there's a table or the floor or something pushing up. If you've got a string, if you've got a ramp, if there's friction, it's either this one, or this one. Usually mu mg on a flat surface, usually mu mg cosine theta on a ramp. But if you've got any other vertical forces, then you got to find the normal force and multiply that by mu to get the frictional force. And just off of the screen, since my toolbar decided to pop up there, the other one would be any external, outside, other force, somebody reaching in, whatever. Okay, so that one's on there too. But that is dynamics. There's a bunch more problems, but they all work that same way.